So this isn't a quiz, clearly. Just trying to see if you can do it. There's more than one way to do this problem. I'd say there's an easy way and a much harder way. If you're looking for the easy way, does the object's center of mass change height? If so, kind of pointing you down a particular path. So I would consider doing it that way. Answer's at the bottom. Square root of 4/3 GL times sine theta. Now, if you can't get to that, you have some work to do. There's not a whole lot here, though. Let's talk about things that we do know. If the object starts from rest, and we have every reason to believe it does, then it starts with only gravitational potential energy. You could use forces to do this problem, but let's be honest, forces has always been the hardest way to do these kinds of problems. And even so, if you used forces, you would eventually have to use net force equals ma, and then probably a motion equation to figure out how fast it's going at the bottom. But energy will do this problem. At the bottom, though, the object has both translational and rotational kinetic energy. Something we talked about in class, that if it's rolling, then the energy will get divided up into both. It's rotating, and its center of mass is moving. But rolling also means that there is a direct relationship between its rotational rate and its linear rate. That's what the word rolling means. Specifically, it means this is true. So in this problem, the amount of potential energy we have, mgh, or in this case, L sine theta, has got to be equal to the total amount of kinetic energy we have at the bottom, which is going to have to be 1/2 mv squared plus 1/2 I omega squared. Now, we've done this before. Not with the rotational stuff like this, and we've done problems that are just rotational. We've done problems that are just linear. This one just has both. It's not a big stretch. But there is more to do, right? It looks like I can't have I in my answer. Well, that makes sense. Our shape, we know, plays a role in the problem. Let's get the shape into the problem. So I can make a substitution there. Any problem with that? Well, I'm asking specifically for the linear velocity. We have two velocities here, the linear velocity and the angular velocity, but since you're being asked specifically for linear, you should probably put the whole thing in terms of linear. We can because we know that it's rolling, which means we're allowed to either put it all angular or all linear. So, a little quick algebra there. And I can have 1/2 mv squared plus 1/4 mr squared times v squared over r squared. That's equal mgl sine theta. Now, this happens a lot in these kinds of problems. You'll notice the r's cancel out. Look for stuff like that. You're going to see that quite a bit in these kinds of questions. And I have two things I can add together because they're both mv squared. So I have 1/2 plus 1/4. I don't think it's much of a surprise, but did you notice m cancels out too? We saw that a lot first semester. That wouldn't happen if we didn't know what the moment of inertia is. If we didn't know what the moment of inertia was, then we'd still have M and R still in there. But knowing the moment of inertia allows us to get rid of some of these things. You should probably consider redoing this problem in terms of I and see what happens. But at this point, I'm just solving for V. And, of course, I get 4/3 GL sine theta. Now, to be thorough, you should replace this with a ring and try again. We know the answer, right? We know the ring should be slower at the bottom. Can you prove it? You should be able to. This should take 60 seconds because you're only changing one thing. You're changing the moment of inertia from 1/2 mr squared to mr squared. We are taking a disk and replacing it with a ring. There you go. And I do mean 60 seconds. You change just one number. Right here. That'll affect this number. That'll affect this number. Right, but that's it. And if you've done your math correctly, okay. There's no M. The ring's slower, right? Where I had 4/3 for a disk, I have 1. 4/3 is bigger than 1. In fact, what if the coefficient of friction was 0? Would the object roll at all?
No.
How fast would it be going at the bottom if there's no rolling? If there's no rolling, or if there's no change to the rotational kinetic energy, then this term goes away. What do you have left? Well, your velocity will be 2 GL sine theta. Fast is just a slide with no friction. Anything else, and the energy gets divided up in some way. But that shouldn't surprise you. What I mean by that is, when you're rolling, you still have a frictional force acting to prevent you going down the ramp. Something we talked about on Friday. That when we look at the forces acting on the object, you're still going to have mg sine theta down the ramp and friction up the ramp. What this should tell you, though, is that the ring has less acceleration than the disk, which means for the same two objects, they will have different amounts of friction. Right? Two objects that may have the same surfaces, same mass, same radius, but friction acts on one differently than the other. I know that we said in the beginning of the year, friction is equal to mu times the normal force, but remember, it's an inequality for static friction. How much friction is used to roll something depends on how hard it is for that thing to roll. So different amounts of friction will be developed depending on the shape of the object not just the surfaces in contact, because friction is on a sliding scale. So I want to figure out how much friction there is to roll, and I want to do it in the most difficult way possible. I don't mean that in a mean way. I mean, you could do what we've just done here to figure out the frictional force. And I'm saying this to you all, you could find the acceleration from a motion equation, because we have the final velocities of a group of different shapes. So you could use a motion equation to figure out the acceleration, and you could then use that to find the frictional force. That's one way to do this problem. And I ask you to do this problem this way in your homework. I also ask for forces. So we're going to evaluate the forces. And part of the reason is because I think it's important for you to understand that in the case of dealing with the forces on an object that's rolling, it's not as obvious as it should be. There's a lot of stuff that we talked about on Friday that I think you should already know. And to put that up on the board, let's just give it a little bit of perspective. I said on Friday that there are a group of forces that act on your object. And I don't need to make it that big, so let's make it a little smaller. And you should be aware of what those forces are and how they interact. So we've got gravity downwards. Oops, no we don't. Gravity downwards. Something like, let's see. Ooh, I didn't want to do that. Trying to get this in the center of the sphere. Does that look like the center of the sphere? It's hard for me to tell from all the other stuff I've got up here. There. So that's mg. There's a normal force. It acts straight up from the surface. And a normal force passes right through the center of the sphere, which is why the normal force does not apply a torque. And we're talking about the situation in which the object is rolling down the ramp. Remember, direction is important here. If it's rolling up the ramp, friction will be one way. If it's rolling down the ramp, friction will be another. It shouldn't be hard to figure out what direction friction is. And there's a couple of ways to deal with that. But if you're having difficulty, think of it this way. Is the object speeding up? Is it rotating faster? If it's rotating faster, then something has to cause a torque for it to spin faster. It's not hard to imagine that if you're releasing it from rest, it's going to start spinning this way. And the friction should be helping to make that happen. Now, this part is the part that I think students have difficulty with. And I've drawn the friction way out of proportion too big. It's just to indicate the direction. The friction is probably a very small amount of friction. In fact, although this is true, we're looking at the very low end on it. It does not take much friction for an object to roll, regardless of the surface. But in your notes, if you want to be able to get this better, things that are harder to turn will require more friction to roll. It's not just about mu or the normal force. This sliding scale responds to inertia. Now, I said on Friday that you can contemplate this problem two different ways. A pivot point at the center or a pivot point on the edge. The true pivot point is the one on the edge. This is where the actual pivot is. That point is at rest. And friction is holding it in place. So in sixth period, we did the problem from the standpoint of the pivot point being on the edge. In this class, I'm going to do pivot point in the middle. We'll get the same answer. One of these is more work than the other, and you'll have access to both of them. Does that make sense? Now, I'm going to do something to make this harder than it has to be. I'm going to do this in terms of I. I am not going to do it based on a specific shape. This is purposeful. If we do this in terms of I, then you have solved it for every possible shape, right? So in the end, you just throw I in and know what the answer is going to be. You can do it for a disc, a ball, whatever. If you start from the beginning with the shape in mind, then you don't really know where the shape affected the answer. So I want to do this in terms of understanding where the shape affects the answer. Now we're going to do our pivot point at the center. And because of that, The net force equations are unaffected by that decision. Net force in the x direction equals ma. Just a quick reminder, that's the y direction, that's the x direction. So when I say net force in the x direction, I am saying mg sine theta minus friction equals ma. That is the x direction. And of course I could do the y direction too if you'd like. Net force in the y direction equals 0. So normal equals mg cosine theta. What I want is an expression for the frictional force. That's what I want. If I solve it for it right now, it would be in terms of the acceleration, which I don't know. Now, our last example, we showed that you could find the acceleration from energy. But we are doing this holistically from force. So knowing that our angle is still theta, and knowing now that we're going to deal with torque, we're going to do this with the pivot point at the center. Again, not the true pivot point, but I'm just trying to show that you can do it either way. Now, looking at the pivot point being at the center, there are 3 forces that act on the rotating object. Let's evaluate each one to see which ones actually cause a torque. And let's remember, torque is R cross F. So, first I noticed that the weight acts at the center. That means that's a torque arm of 0, so the weight doesn't cause a torque. Everybody understand? Any question about that? Now, when you put the pivot point at the edge, it does, but we're putting a pivot point at the center. So next, let's consider the normal force. The normal force acts at a distance r away. So there is a torque arm, but the normal force acts at an angle of 0 degrees with respect to the torque arm. So that's a sine of 0, and that means the normal force applies no torque. Which leaves just the frictional force. The frictional force acts at a distance r away from the pivot point with a size force F, and that's going to be sine 90 degrees because this is a right angle and has to be. And this has to equal I alpha. All right. We're trying to find an expression for the frictional force. Currently, we have 2 expressions that have friction force in it, but they have a variable that I really would prefer not to have in my answer. So I need to eliminate it. One way to eliminate it would be to express them in the same form. Since the object is rolling, just like V equals omega times R is defined to exist for rolling, that means this has to be true too for rolling. And since we're saying this is rolling, I can make that a substitution. I just have to pick which way to go. Do I want to do it angular or linear? It doesn't make any difference because we're going to be eliminating that from those 2 functions. So there's no one way that's better or worse than the other. So I'm going to do them both in terms of the linear. So these are my 2 functions. I'm going to bring them together by setting them both equal to A. And then, actually, no, I think I'll do it different. I think I'll do R squared F over I equals A from the torque equation. And I'll plug that in to the force equation. Is that fair enough? All right. mg sine theta minus friction equals m r squared F over I for alpha. I'm sorry, for A. All right, I need to solve this for f. So I don't know how you want to do that. I know how I'm going to do it. I'm going to get the terms with f to the same side of the function. So mg sine theta equals f plus m r squared f over I. Any question about that? Okay. Factor out the f. Is that good for you guys? So factor out the f. 1 plus mr squared over I equals mg sine theta. We good so far? All right. Solve for f. We good? Now, do you notice that the bottom of this fraction has no units in it? I has got to be in kilogram meter squared, and the top of that is kilogram meter squared. You notice that? Also, you all are aware that the shape of an object with the largest moment of inertia would be mr squared. You understand that too, right? So when you think of the different things that can roll, there's a hoop, a disc, a hollow sphere, a solid sphere, now, I don't know if you're capable of doing this kind of in your head, but this fraction for the object that's most difficult to turn would be 1, mr squared. You see that okay? But for the object that's easiest to turn, it would be 5/2. Right? Because it's going to be inverted. Still adding 1 to it in the denominator. Do you see that as well? Now, that means the denominator gets bigger when the object is easier to turn. What does that do to friction then? It gets smaller, right? If the denominator is getting bigger, my whole value is getting smaller. So the easier my object is to turn, the less frictional force is required to turn it. But most importantly, what I really hope this shows you is that first, how much friction does depend on the object's inertia, right? Mass is there. But the shape plays this interesting role here. The mr squared cancels out. It's just that number out front that matters. Now, be thankful we did it this way. I say that because, now, I point this out for a number of reasons. First, this is actually how the object is behaving. This is where the friction is coming from. And it shows quite clearly that the easier the object is to turn, the more the less the frictional force is. And it shows you why and where that occurs. But ultimately, there's no way to get the frictional force using this. You just can't. The only way to get it is this way. I asked you to recreate this in your homework a couple times. You now know how to do it, or you should have at least a method to do it. There's only one more thing really that we really need to discuss, and that's how do you transition from not rolling to rolling. There's lots of variations on a theme too, Like, how does this look different if you're rolling up a ramp rather than down a ramp? How does the friction change? And you should be looking at all of these different things. These variations make sense. Like, let me ask you a question, if you can do the answer to this one, because I think this one matters. If I roll an object so that it has a velocity in this direction and is rolling this way, and it rolls up the ramp, what direction is friction acting? Draw a picture. If it's rolling up the ramp, is the friction on this object up the ramp or down the ramp? No, that's my question. You have to answer it. You can't tell me what. Oh, okay. Now, I'm not trying to make this hard, but there's a very simple answer. But you have a choice. Flip a coin. Is it up or down? Is the friction this way? Or is the friction this way? Now, before you answer, is the object's rotational speed becoming a bigger number or a smaller number? I mean, if it's rolling up a ramp, is it going to be speeding up on its way up the ramp or slowing down on its way up the ramp? Now, if you know the answer to that, which one of these will cause the rotational speed to get smaller? It's up the ramp. When an object rolls up a ramp, the friction is also up the ramp to cause a torque to make omega get smaller. Gotta think about it.